Everyone, myself Amit Timilsina. I'm working in the modeling sections of this project. So I will go through a little bit about the model as well as how we are going to use in this project. So I will start with what is the model. So model is the mathematical expressions of real world processes. So what is the real world processes then? So in any system, there are so many components, like in our farm, there is crop, soil, as well as the animals, right? So they are interacting with each other. I mean, many inputs and outputs are also interacting with each other. So that is the real world processes. And if we that express those processes with mathematical equations, that equations can be used in the model and build the model. And the model needs input to provide the output. So what is the input and what is the output? So we need to figure out it. So I would like to give one example. So we use the Google map, right? So what is the first thing we do with the Google map? Right. So we will put the address, right? So then what it will give?
The directions of where you're at, where your address, where you want to be.
Right. So those addresses are the input for the Google map. If we consider Google map as a model, right? And the directions as well as also the time to take that from one location to reach from the one location to another location is the output of the model, right? So the integrated farm system model is the model we are going to use in this project. And this is developed by the USDA. So after they have used like the 25 years of the research data to build this model. So it also needs the input. So what are the inputs? Like the soil. We talk about the soil information, right? So it could be soil pH, it could be soil carbon, or the major nutrients like nitrogen, phosphorus. So this kind of the information. And the weather information like temperature, precipitation, humidity, and the crop, dairy, machines, storage, as well as the cost related information. So these all could be the inputs for the model. So when we provide these inputs to the model gives us the output. So it could be, there could be so many outputs of the model, like grain yield, harvest yield, milk yield, feed qualities, GHG emissions, soil qualities, as well as the profit and loss from our system. So that's how the model works. It takes the input and then provides the output. So these informations we collect from different farms, and based on that, we will get those outputs, and that outputs can be used for the various purposes. Or it could be like, let's say we can compare one field to the another field, one management practices to the another management practices. And also, it is also useful for the planning processes. And more importantly, we can know what if the certain management practices we adopt in our field, is that profitable or is that non-profitable? So we talk about the soil, also about the forest, right? So that's the part of the one whole system. And it's a little bit easier to understand the single component. But when we put all the components together, and in these processes, there are so many things or so many processes going on, and they are interacting with each other. So in this case, it's not easy to say if we change the one component, so what is going to happen with the other components? How they will interact with each other. So in that case, model is very useful. So in one cases, let's say we measure the GHG emission, right? So we measure with a certain interval, like 1 month or 2 months or 3 months. But if we use the model IFSM, it will give the daily values as well. So that cannot be done with the in the field conditions, right? So how the IFSM has been used before? So basically there are few areas where IFSM has been used. The first one is like the production potential. So what will be the production potential with the certain farm types or certain management practices, like simulating the forage crop production in the northern climate with integrated farm system model. Similarly, the greenhouse gas emissions. I already talked about this, and the profitability of the farm. So this is the one research which is conducted in the northern Great Plains area, and they have compared like what if they use cattle manure and the urea fertilizer. So you can also see here they have compared the performance in two different time periods as well. So from 1990 to 2015, and also from 2014 to 2065. So that means model is also useful to know what happens in the future. So we can compare with this with the any current management practices, or also we can alter the different management practices and see the impact. So in this case, they try to find out what will happen with the corn grain productions. So we can see here the productions is higher under the inorganic fertilizer in the future. But at the same time, the other parameters like energy use and the greenhouse gas emissions are higher with the inorganic fertilizer as compared to the use of manure. So that's how we can compare the different management practices. And there is always a trade-off between or among the many factors like yield, greenhouse gas emissions, leaching of the nutrients. So this is the another research conducted in the Canada. So what they have tried to understand is if we allocate the corn field for the grass production, so what is going to happen with the total forage yield as well as the milk yield. So in that case, if we allocate more corn area to the grass land, so in that case, the whole milk yield is going to decrease. So the model itself is built with the many years of the research, and there is like based on that research, they have already calculated certain average values for to use in the model. If we don't know the certain values of the certain factors, let's say we know the soil types, right? So silty loam. But in that case, from those 25 years the research or from the different locations, they have already put certain values of that silty loam clay or clay loam soil. So the different factors, certain average values are there. So if we don't know those values, in that case we can use the model values, but those model values could be different or the similar to our observed or the real values. So we always try to use the real values so that the model gives us the good results, reliable results. So over to
Yeah, just to give you a sense of what this stuff is about, just to extend that a little bit, you know, we measured a lot of things on your farms. Some of it is easily lends itself to those soil comparisons. Some of it, like measuring manure content, is so that when we simulate a farm in this model, we can ask, is the manure we're seeing going on these fields similar to or different from, or are the forage quality and components the same or different from what the model would have assumed. And then, yeah, so we're now going to show you like what are some of the highlights of some of the results of the actual analysis we drew from our partner farms and compare that to the numbers that you'll see the model would use if we didn't know another number. There's 1,000, 10,000 numbers in model, right? They can't replace everything, but we see some key points where reality checking is going to be interesting and comforting to know that we're getting in the right ballpark. That's what we're doing now.
So I'll show you forage, and then there's some results from manure as well. In the model will give us seasonal information for forage. So we have late spring, summer. There's different seasons that we could choose in the model. And so we collected those and to compare. So this is the late spring, and this is only hay and pasture. So there's no other type of crop here. So that's why it's just C2 and D, the farm types. So in terms of crude protein, it was variable between the farm types. Overall, we could say it's probably the model was a little bit higher than what we actually saw for late spring. For that, we didn't do the degraded protein, which is something that was in the model, but we didn't analyze for that. We can calculate it. We just didn't do that yet with the data that we have. For insoluble protein, also the model was higher, in this case, higher than the crude protein. So from 2 to less than 1, it's actually what we saw. TDN, total digestible nutrients. Also, again, we see the model higher, assuming that we have more than we actually are seeing in the field. But for phosphorus and potassium, the model was very on target, or primarily for both of these farm types. Late spring, then we put summer there. Summer for protein, higher for the type D, which would be graze pasture primarily. For the hay types, mostly was closer. Again, we see that we have lower insoluble protein, but now it's a little bit closer than the model expected or thought that we had. TDN now closer. So for summer, it seems that the model is getting closer to the real values overall. Phosphorus and potassium were also good here for summer. And then we have early fall results. We don't have for C2 there, we have for D. Again, then here the model expected even higher protein than we saw. So early fall, we have lower protein than the model expected, lower insoluble protein too. We actually had more TDN now here than the model showed us, or assumed. Phosphorus and potassium were again on target. So for these two parameters, it seems that the model is doing well for regardless of the season. And there's some variation, but overall, the model seems to expect that we have higher quality than we actually are having in the field. That's kind of the overall conclusion. Can I do some marketing real quick for the forage? We can analyze forage samples in my lab now. So if you want to send us your forage samples, we can also do almost all the cover crops, pasture, graze, hay. We can do those. We can do all kinds of forage quality analysis in the lab. It's going to be at a lower cost than a normal, commercial lab. We're here in Columbus. My lab is in Columbus. And what else am I going to say? We're going to have different packages for different things if you want to see. I don't have a website in place or a form yet, but if you're interested in sending us samples, the lab can do the analysis already. We just don't have all the pretty website. So you can just contact us and we can work on the shipping and send us your samples. We can analyze for all of this and send you results. Also, I remember what I was going to say. For corn samples as well, corn silage, fermented and unfermented corn silage, we can also do in the lab. So forage quality for all these crops. Okay, going back to the manure results.
Advertisements are.
Yeah. Pause for the commercial.
Like watching a YouTube video. Yeah.
Real quick ad that you can.
Let's subscribe here.
So for manure, I'll show you first that this is not comparison to the model. This is our actual results. And we did for liquid manure versus the stacked manure across all farms. So the variability here will be farms. All of the farms are in time because we collected at different times of the year.
One really important point, I did not make at the very beginning, but I think you may appreciate, we're only looking at cattle manure.
Oh, yeah.
So none of the fields we're studying have swine manure or poultry manure. None of the fields, a sample analysis we're running. I know in some parts of Ohio, those are really significant sources of manure, but just because the ruminant, to simplify one thing, we just decided to look at fields that are receiving, when they're receiving manure, they're receiving exclusively, usually, but or at least predominantly.
So dry matter, obviously the liquid manure was lower, and then we have more variability in stacked manure. There's different types of dry matter and moisture available there. pH, they were both, if you're gonna compare liquid versus stacked, they are very much close, and around 7-9 pH for both types of manure here. Yeah, then we have nitrogen content, and that is organic nitrogen content. Total nitrogen versus the organic nitrogen content percentage in your dry matter. So we see that liquid, there's more variability first. In the liquid, we have higher values for total nitrogen, possibly higher than the stack, but then the stack manure had more organic. More of that nitrogen was organic in the stack manure than in the liquid, which could be associated with loss. Liquid manure is losing special nitrous oxide. There's nitrous oxide emissions coming out of liquid manure because of the wet conditions. And so it could be losing this manure, the organic manure, and then in the stack is concentrated there. And then here we see the different results for phosphorus and potassium. So variability is higher for the stack manure in phosphorus, and they are kind of the same, although the variability kind of makes it difficult. And then for case that we have an outlier all the way over there, bring that could also be bringing the average a little higher, but there's lower, a little bit lower contents of in the stacked manure there. So this is just an overview of the liquid versus stack. So now we take this to the model. What was the model expecting? What we saw? Here we don't have seasons. The model will not separate by spring, early fall, all that. We have manure type in terms of animals. So we had dairy, beef, cattle, and that we were able to see in the model. I'm showing you the dairy results only. And then we have the different types of farms that had manure, B, C1, C2, and D. And then an average across all of them, because that's what the model would do. It would bring all of that into a model, into an overall average. So that's what we're going to compare. Although you can see the variability for farm type there too. So in terms of dry matter, the model thought that we had much lower, that our manure was primarily dry. Wet, and then we had 23% of dry matter actually in the valley in our observations on average. Nitrogen content model thought that we had almost 4%, and we have 2%, so kind of half in reality. Organic nitrogen content, we are higher. The model estimated 70%. We are actually at around 86. Some types going up to 90% of organic nitrogen. Phosphorus content. The model now is lower than our real values, and for potassium, closer, a little bit lower as well in the model results. Questions?
So what is the CN ratio of
The what?
CN ratio, carbon to nitrogen ratio?
I didn't add it. I had that figure. It's not in here. I don't remember. I have to check. I thought I had it. But yeah, it's a good question.
So we have 4 different farm types actually. So with the model, if we want to compare this farm type 1 and B, which is different with the manure application, right? So farm type B receives manure, but not farm type A. So with this, what we can do, if we use the manure in the farm type A, so is that going to increase our grain, or is that profitable? So what is the impact on the GHG emissions? And also what is the impact on the nutrient loss as well as the soil fertility. So these kinds of the things we can predict or estimate using the model. Because the farm type A and B are different in terms of soil, weather, as well as the other different management practices. So the result could be slightly different or the same if we change the different management practices among the different farm types. So that's the real use of the model.
One other thing I would say though, equally important, so the way I think about it, I'm a simple man, so may not understand all the complexity, but rather than having a single model, I've been pushing for us to have 5 models. So there's a type A model that's parameterized to the type A fields and farms that we see, a type B farm. If you've been interviewed, one of our questions this winter has been, let's see the whole picture. So how many fields of different types, what proportion of them are tilled and receiving manure if you're a type B or C. We'd have then a representative farm. Your individual farm won't be modeled, but with a representative of a type B farm that will bring to this model. And once we have 5 of those models, we can do these comparisons and sort of see what their relative performance is. But certainly on economics and to some degree on other things, trying to simulate how those different farm types are going to be impacted by different future markets. So if crop prices are going to be different, if you assume some futures in which you have really high or really low crop prices, if fertilizer prices are radically different, we'll be able to sort of see how that affects these different farm types. How will they be in a world in which, let's say there's payments for carbon, what that might mean in terms of adding that to the bottom line for these farms. We don't have any of this done. We've got the samples, we got the analysis, and we're beginning to really flesh out. This spring and summer, we are going to spin up some versions of the models just to kind of get the bugs worked out. And then after 2 seasons of data, we'll be in a good position at the meeting we have with you in about a year to kind of play with the model a little bit. And we really think it's important to play with it in front of you so that you can give us some reality checks. Like, is this stuff making sense? So there's some different what ifs we could ask for the model. What are some, things you're curious about? If we have a, wetter future, what's that wetter future going to mean in terms